Dear students, welcome back to the DFT video. In this video, we are going to introduce one of the most important DFT technique, the internal scan technique. Because scan is such an important DFT technique, so we have different scan available for different designs. For flip-flop based designs, we have Mux-D scan proposed by Stanford in 1973. We also have clock scan proposed by NEC in 1968. For latch-based design, we have LSSD proposed by IBM in 1977. These techniques will be introduced in our following videos. In this video, we will first talk about general concept about scan. The idea of scan is to connect internal flip-flops or latches as a shift register so that we can control and observe the internal flip-flops or latches in test mode. Please note that we still want to remain the original circuit function in normal mode. The idea of scan was first proposed in 1970s by Stanford University and other companies. Scan remains one of the most important DFT techniques for synchronous digital circuits. The bottom two figures shows how we can insert a scan chain into a design. On the left-hand side, this is an original design before scan insertion. The yellow squares represent non-scan flip-flops or latches. After scan insertion, we replace those non-scan flip-flops into scan flip-flops. As you can see, the orange squares are larger in area than the non-scan flip-flops. And the second step is that we need to stitch those scan flip-flops into a chain. In this way, we can scan in our test pattern and we can scan out test response in test mode. This procedure is called scan chain insertion, or it is also known as DFT insertion or DFT synthesis in the design flow. This slide introduces the concept of scan flip-flops or SFF. Please note that we will use flip-flop as an example in this video. For latch-based design, the concept of scan latches is very similar. For scan flip-flop, we have four important pins: scan input pin SI and the scan output pin SO. These two pins are used to connect the scan chain as a shift register. And then we also have a data input pin DI and the data output pin DO. These two pins are used to connect scan flip-flop from and to the logic. Please note that the DO pin and the SO pin sometimes can be shared as a same pin. A scan flip-flop has two functions. It can perform a shift or a capture. The circuit with scan chain has two operation modes: the normal operation mode and the test operation mode. In the normal mode, scan flip-flops are configured to perform capture. So they capture the response from the logic and they apply their response to the logic. So this is exactly the same as the original circuit. In test mode, the scan flip-flops are first configured to perform shift operation, so we can shift in our test pattern. And then the scan flip-flop are configured to capture the response from the logic for one or a few cycles. And then we can configure the scan flip-flop to perform a shift out operation so that we can observe the values in the scan flip-flops. Now let's see an example. On the left-hand side, we have an original circuit with non-scan flip-flops. After scan insertion, we replace these two flip-flops by scan flip-flops, and we have a scan chain inserted into this circuit. Now, in normal operation mode, the scan flip-flop is actually the same as non-scan flip-flop. In this mode, the scan flip-flop will capture data from the data input. Suppose that the scan flip-flop 1 is initially 1 and the scan flip-flop 2 is initially 0. And we apply a 0 at the primary input. So we can see that the output of AND gate is 0, and this is also 0. So the output of OR gate is 0. After 1 clock, the data will be captured in the scan flip-flop. So now scan flip-flop 1 is 0, and the scan flip-flop 2 is also 0. This is exactly the same as the original circuit. Now, in test mode, suppose we want to detect a stuck cat 0 here. So we would like to shift in our test pattern. The scan flip-flops are first configured to perform a shift operation. Because we want to activate this 4, so we will need a 1 at the primary input, and also we will need a 1 at the scan flip-flop number 1. Also, we want to propagate this 4 effect through the OR gate. So the side input here must be 0. So we want scan flip-flop number 2 to be 0. So we can shift in a test pattern 1, 0 into this scan chain. This figure shows the flip-flop state after 2 cycles of shift. And then we can have a 1/0 at the output of the OR gate. And then we configure the scan flip-flop as capture. So we can capture the response into the scan flip-flop 1/0, which means that for the good circuit, the value should be 1, and the faulty circuit, the value is 0. And then we can perform a shift out operation of 2 cycles. At the output here, we can observe 1, 0 at the second cycle. In this way, we can detect this stuck at 0 in test mode. Please note that this fault was originally untestable in normal mode. Do you know why? Please think about it. Now it's time for you to work on the quiz. Suppose we want to detect a stuck 1-4 here. Please pause the video and fill in the question mark. Okay, have you finished? If we want to activate this 4, we would need a 0 here. So this flip-flop, we need a 0. To propagate this through the OR gate, we also need a 0 here, so we can have either a 0 here or a 0 at the primary input. Either one of them is fine. And then after a capture, we can capture the response here, which is 0/1. For good circuit, this flip-flop should be 0. For faulty circuit, this flip-flop is 1. And this flip-flop is supposed to be 0. Now, we shift out the contents and we are able to observe a 0/1 at the end of the second cycle. Have you get it correctly? As we can see from the previous example, scan can actually turn the sequential circuit into a combinational circuit in the test mode because the flip-flops are fully scannable. So we can fully control the output of the flip-flop. We can also fully observe the input of the flip-flop. So actually we can ignore these flip-flops in test mode. So what ATPG really sees is only a combinational circuit model, where PI are primary inputs of the original circuit, and the PO are the primary outputs of the original circuit. And the scan flip-flop data output now becomes pseudo-primary input for this combinational circuit model because they are fully controllable. Also, scan flip-flop data input now becomes pseudo-primary output of this circuit model because they are fully observable. So for ATPG, we only work on this combinational circuit model. This is a very good news. Scan makes ATPG a lot more easier. Now it's time for you to work on a quiz. Suppose we insert the scan chain into the circuit. So we can actually remove them in the ATPG. Please tell me which of the pins are primary input, primary output, pseudo-primary input, and pseudo-primary output. Question number 2. If we want to detect this stuck at 0/4, what are the values of this question mark? Please pause the video and work on this quiz. Okay, this one is easy, right? Primary input is A and primary output is Z. They are the same as the original sequential circuit. For scan flip-flop number 1, it corresponds to the pseudo-primary input number 1. For scan flip-flop number 2, the output is pseudo-primary input number 2. To detect this stuck at 0/4, we require a 1 here and a 1 here. So PPI number 1 must be 1. and the primary input must be 1. To propagate this fault, we need the 0 here, so PPI number 2 is 0. At PPO number 2, we can now observe 1/0 here. In this way, we can detect the fault. So now we only work on this combinational circuit model, which is much more easier than sequential circuits. Scan is such a good, powerful test technique, but it does not come without cost. The advantage of scan is that we can have systematic DFT. It's not ad hoc DFT. So we have many automatic tools to help us to insert scan chain automatically. Also, it makes ATPG easier so that the runtime is faster and the fault coverage is higher. If you want to know more details, please see video 11.4. With scan chain, we can do silicon debugging or diagnosis more easily. Silicon diagnosis means that after manufactured some prototype chips, we can use scan chain to help us to debug. If there is anything wrong with the prototype chip, we can shift out the contents in the flip-flop and observe their values. So this is very good for debugging. But there are some costs associated with scan. First of all, we need more area for a design with scan inserted, because the scan flip-flop is larger and we need some area for routing of the scan chain. Typically, 5 to 10% of area overhead is acceptable. Second, we have performance overhead because a scan flip-flop has longer setup time and hold time. So the performance of the chip can be degraded after scan insertion. And also we need to pay pin overhead. We have more pins such as scan input, scan output, scan enable pins, scan clock pins, etc. Please see the other 2 videos for details. Also, a circuit with scan chain inserted would cost more power. And we also need extra design efforts to insert a scan chain and verify the scan chain. Please see these 2 videos for more details. Now it's time for a quiz. Suppose we insert a scan chain into this circuit and replace those non-scan flip-flops into scan flip-flops. Given this gate area table, please calculate the area overhead of the scan DFT. The area overhead is defined as the incremental area over the original area before DFT. Now please pause the video and calculate the overhead. Okay, are you finished? In the denominator, the original area of the circuit is 1 OR gate and 2 AND gate and 2 non-scan flip-flop. So that would be 19. After DFT, we have 2 scan flip-flop. That would be 21. So the area overhead is 2 over 19, which is approximately 10.5%. In summary, scan is one of the most popular DFT techniques for digital VLSI, and a scan flip-flop has 4 important pins: scan input, scan output, data input, data output. A circuit with scan has 2 operation modes. In normal mode, scan flip-flops capture data from the logic. In test mode, we first shift in the test pattern, capture the response from the logic, and shift out the contents in the scan chain. Scan makes ATPG much more easier, but the cost is area overhead and the performance area overhead and many other more. At the end of this video, I would like to ask you questions. We mentioned that this fault was actually untestable in normal mode. Please explain why. And the question number 2, since it's untestable, why do we care about it? Please think about these 2 questions. Thank you.